Hello guys, welcome back to my YouTube channel. I'm Nafta. In today's lecture we're going to talk about electromagnetism, and in the previous lectures we've been saying there's a correlation between electricity and magnetism, like the two cannot be separated and that they have a very significant relationship in physics. Now, first subtopic we're going to talk about is a charged particle in electric field. That is the first subtopic we are going to talk about. Consider an isolated electric charge placed in an electric field. We consider an isolated charge placed in an electric field, and this is our electric field. This is the positive plate, and this is the negative plate. Now we have our charge, which is an isolated charge placed at this point. Let's call our charge Q. Now, of course, this is a potential. Now, this charge, when it released at this point, it will tend to accelerate towards the positive plate. We'll see our charge moving towards the positive plate. Now, our charge has a negative charge. It's negatively charged, and therefore it will tend to move to the positive plate. Now, our charge will move at an electric force, and our electric force, that is the force due to electric field, is given by the electric fields times the charge. But from Newton's second law of motion, we know force is equal to mass times acceleration, because our charge here, which is an electron, could have mass. Okay? Now, if the mass, remember, if we maintain the mass to remain constant, that is, we assume the mass of the electron does not change, and therefore acceleration will be changing, we can say mass times the change in velocity. Again, that is if velocity is the factor that is changing. So if this particle, our charged particle, is moving at a velocity nearer that of light, both the factors will be changing. That's according from Albert Einstein's theories of relativity. And therefore, we are going to say velocity will be equal to the change in mass and velocity. Both factors will be changing. And therefore, to work out this part, we use now applying product rule. We apply product rule to work out this part. Now we'll say force will be equal to, we maintain this constant and we differentiate the velocity factor, that is m. So applying product rule, we'll maintain this constant and then we differentiate the velocity factor, and then this will be the differentiation, and then we maintain v constant, we differentiate m, and this will be our conclusion. Now let's see the work done in moving this charged particle from this point, let's call it point 1 to point 2. So work done in moving the particle from point 1 to 2. Now, work done is equal to, remember we know work is equal to force times distance, and therefore we can say work done to move the particle from point 1 to point 2 is the force times distance. But we had said the force to be equal to, that is from distance 1 to 2, force we had said it to be equal to EQ dx. But we know that potential is equal to ED. Now, bringing E out, because it's a constant factor, we'll say work is equal to E, then we integrate from point 1 to point 2, then we say this one. Now, we'll say that we say work is equal to Q, which is a constant factor that does not change from point 1 to point 2, then the electric field dx. But when you differentiate this part, it becomes d, or x. It becomes x. Now, that is electric field times the distance. We decided earlier this part will be equal to v, and therefore we can say work done to move a charged particle from point 1 to point 2 is qv. Now, having done that, we want to find out the velocity at which that particle is going to travel. Now, we'll make this assumption. We'll say that work done will be equal to the energy required to move the particle from point 1 to 2. So work done, which is QV, will be equal to, and the work done to move, so we have said is QV, and the energy required, the energy of movement, the energy of locomotion is kinetic energy. We'll say this energy, let it to be kinetic energy, and therefore kinetic energy is given by half mv squared. Now we make v the subject of the formula. That means we'll cross multiply by 2 over 1, then 2 over 1, such that this one and this one cancels out, and then we multiply by 1 over m, such that this one and this one will cancel out, and here the same thing we have done here, we'll do it here, 1 over m, and therefore we'll say it will be 2qv over m will be equal to v squared. Now, finding out the square root in both sides, we'll say velocity is equal to 2qv over m. That will be the velocity. Of course, positive or minus, but because velocity we can say it positive or minus because velocity is a vector quantity. Now, we want to talk about the movement of that electric field again in a uniform electric field. The movement of that charged particle in a uniform electric field. Consider that is the moving that charged particle, charged or moving charge in a uniform electric field. As we said earlier, we'll take this to be our positive plate and this to be our negative plate. Now we have that charge released at this point. Our charge will tend to move in this direction. Of course, if there were to be no electric field, this could be the movement. Now, and of course, this could be the distance our charged particle covers in the vertical direction or in the vertical axis, and in the horizontal axis, this could be our distance it's going to cover. Let's call it x. Now, earlier we had said that the electric field of that charged particle will be equal to V over D, where V is the potential and D is the distance. Now, to find the time this particle takes to move from this point up to this point, we consider the horizontal, that is the vertical component. We'll say assume this to be the velocity which our particle is going to move in the vertical component, and UO to be our horizontal velocity. Now, the time it takes to move from this point to this point in the vertical axis, it will be, time will be equal to, we know time is given by the distance. Let's say this distance from here up to here is L over velocity, and the velocity we said to be Vx. Therefore, we will say, and this is the time it will take to move in the vertical component. Now we find the time it takes to move in the horizontal component. The time it takes to move in the horizontal component. Now it will be, remember, the acceleration this particle attains as it moves along those positive plates, let's call that acceleration as AY. Now acceleration is normally equal to force over m, and we said force to be equal to QE over m. Remember, in the previous we had said force due to the electric field is equal to QE, and this can be said to be equal to, remember we said that V is equal to ED. That will be our value for potential, and therefore replacing this one, it will be equal to, E will be equal to, that is divided by D, we divide by D, V over D, and therefore if we replace this, it will be QV over MD. That is the acceleration. It's the acceleration of a charged particle. Now, in the horizontal axis, as we said, a charged particle will be moving in the vertical component, that is in the vertical axis, and we are also going to see the movement along the horizontal component, and therefore we will say that the Vy, being the horizontal, we decide ours to be UO. That is the horizontal velocity, will be given by, that is, applying Newton's first law of motion will be equal to Vy, that is the initial velocity, plus the acceleration of the particle, which we said is to be AY times time. Now, the initial velocity of our particle is normally 0, because our particle, it said, will put it there, and therefore it was not moving, and then we'll say the initial velocity along the horizontal component is 0, plus the acceleration we said we derived it to be QV over MD times time, and the time we derived here as the distance over the velocity in the vertical component. So L over Vx. Now this will become a QVL over M dVx. That will be the velocity our particle is going to move in the horizontal axis. Now we had said our particle, we see it, there is an angle here, and therefore how can we find this angle? We have derived the horizontal component, and we derived the vertical component. Now time is going to be equal to, we're finding that angle. If I extract that triangle, we saw a particle exhibiting the horizontal and the vertical behavior, and this is our angle. Now we set this to be this is a UO and this is Vx. Now to find this angle, we'll say tan theta will be equal to Vx over UO. But what was our Vx? That is the velocity in the vertical axis. The velocity we said it to be Vx over the velocity in the horizontal is QVL over MdVx. Now this part here is a double division, so it will come up here and we'll say it will be equal to Vx squared Md over QVL. Now we can say this to be the angle, that is tan theta. Now to find the angle itself, it will be equal to tan, that is theta, will be equal to tan inverse of Vx squared Md over QVL. That will be the angle. Remember, V here is the potential and Vx is the velocity in the vertical axis. Now, let's talk about static electric field in dielectric materials. We have finished with a charge particle in a uniform electric field. We have seen its behavior, we have found it is a velocity, the vertical and the y components, and we have calculated the angle the particle is going to subtend when it moves along that uniform electric fields. Now, let's consider static electric fields in dielectrics. And I'm going to define a dielectric material as a material which allows electric fields to flow. So dielectric material is one that allows electric fields to flow. Now, we have the properties of such a material for it to qualify to be a dielectric. One, that is the properties of this material. One, it must be homogeneous. That is, a material is said to be homogeneous if its physical characteristics such as mass, density do not vary with time. That is, from point to point, a material whose physical properties or characteristics such as mass and density do not vary from point to point. And then two, it must be linear. A material, that is the property of linearity, a material is said to be linear if the magnetic flux density is directly proportional to electric fields. And we are going to see this formula very important as we proceed with our lecture. So we can say, if we introduce a constant here, the magnetic flux density will be equal to permittivity, which is, I can call it mu naught E. And the permittivity of free space we know is equal to 8.85 times 10 raised to power negative 12 farads per meter. Now, another property is isotropy. And isotropy refers to the properties of a material becoming independent of direction. Materials' property do not vary with direction. Now, let's talk about electric dipoles and dipole moment. Electric dipoles and dipole moments. A dipole, I want to define what is a dipole, is is two equal point charges, two equal point charges with opposite sign separated by a distance L. So if we have this as the positive and the negative charge, now when these two get separated by a distance L, this forms a dipole, because we will see fields emerging from this point, originating from this point and ending at this point. So this is the fields are originating from this point and ending in this point. That is a dipole. Now we want to calculate the electric potential of such a dipole from a distance. Let's call that distance to be point P. Let's move to the next page. Now we have this as the positive and this is as the negative. Remember, it's a dipole we're talking about, and it's separated by a distance L. Now we have a point P here. This is our point P. This way. Now we'll say this distance to be R, and this distance to be R1, and this to be R2. Now, of course, this is when if I partition this is now consider, let's say this the distance from here up to this point is a half, is a half of the whole of this distance, that is L over 2. Now if this is the angle, at this point, then therefore we'll say the distance from here up to here will be equal to L over 2 cos theta, and the same as L over 2 cos theta, because this distance from here up to this point, let's say it to be equal, and therefore we know potential from a particular point is equal to Q times the charge over the distance, where Q is a factor, that is a charge factor which normally has a value, and we can say we want to calculate the potential of this charge 1, call it this as charge 1 and this to be charge 2. Now V1, that is the potential for charge 1, will be equal to KQ1 and then R1, the distance for R1. That is the potential of charge Q from point P will be equal to KQ1 R over R1. Then the potential of charge 2 from point P will be equal to KQ2 over R2. But we, from definition of a dipole, we decided it to be those are two equal point charges separated by a distance L. Now we can say Q1 will be equal to the negative of Q2, because we said they have opposite signs. Now the total potential for these two charges will be equal to V1 plus V2, which is Q1 R1 plus, but this is negative KQ2 R2. Now we can say this to be equal to the charge Q, because both charges are equal and they have opposite charges, and therefore due to that opposite charges have introduced a negative here. Now Q, KQ R1 minus KQ R2. Now factoring the common factors out, KQ is a common factor and we will have 1 over R1 then minus 1 over R2. But if R1, R and R2 are very far from P, then we will say R1, R and R2 appear to be parallel, and therefore we will say R1 to be equal to, the distance for R1 will be equal to, look here, if these all of them appear, R1, R and R2 appear to be parallel, that is from if P was to be at a very far distance, then we'll say R1, you know, from here up to this point is R, and therefore we are going to see there's a particular distance from here up to here such that will be equal to R1, and that distance we can subtract it such that we want to see R1 will be equal to this distance, so this distance from here up to this point minus this smaller distance, which we said it to be L over 2 cos theta, will be equal to R1. Now our R1 will be equal to R minus L over 2 cos theta, and R2, look here, from this distance up to this point is R. Now for R2, you know there is a particular distance, you can see it has been, like we are seeing it being extrapolated, there is a distance, a small distance being added here, and then we'll add it, and therefore we'll say R plus L over 2 cos theta. Now inserting these values we have got here for each R1 and R2 to their correspondent values here, we are going to say Q, that is, remember we are calculating the potential of 2 point charges from a distance, and therefore it will be into brackets 1 over R1, and our R1 we set it to be R minus L over 2 cos theta. So R minus L over 2 cos theta minus 1 over R2, and our R2 is R plus L over 2 cos theta. Now working this out, we are going to say the LCM for this is 2 cos theta, and therefore we will say KQ will be equal to 1 over 2 cos 2 theta will go in here, that will be 2R minus R over 2 cos theta minus 1 over, remember here it was plus R, as we had said, R2 will be equal to R plus L over 2 cos theta. So here we forgot how to R, I've added it, and here because it is a plus, when we work out the LCM is 2 cos theta, it will be 2L plus L over 2 cos theta. Now because this is like E, when you look here, this is a double division of a point, so now this one becomes a multiplication, it becomes our numerator, it will be equal to KQ 2 cos theta, now 2L this way over, we want to bring these two together because we have said these two I've placed these two up here, and by saying I found out their LCM, which it will be 4r squared minus L. Now if r is much greater than L, and therefore we are going to say this will be a factorless, and therefore we will say potential will be equal to kq 2 cos theta over 2L times 2L over r 4r squared. Now this 2, when you multiply them, remember this is a constant and this is a constant, this becomes 4, so it cancels here once. This is like 2 times 2, which is 4, and then it will cancel with the 4 in the denominator. Now we are going to say, bring this L here, it will be kql cos theta over r squared. Now I want to separate this into this as this kql. I want to bracket this one 1 over r squared cos theta. That's what I wanted to separate them. Now I want to define the following terms. K will be a constant given by 4 pi times permittivity of free space. Now QL, we call it dipole moment, and 1 over r squared will be equal to our distance factor, and cos theta is our angle factor. Now in our subtitle we said we are going to discuss about electric dipoles and dipole moment, and we have done with an electric dipole. We have said much of it, and then we have talked about the dipole moment. This is what we wanted to live, and then we have seen everything as it is worked out. Now guys, for those who have not subscribed, please subscribe, like, comment and share. I'll meet you in the next video where we shall be talking about the torque. When we have a torque, what will be the torque of a dipole in a uniform magnetic field. Then we'll talk about inductance, then we'll talk about capacitance, and then we'll talk about magnetostatic and magnetomotors. All of those factors I shall be talking them in the next video. Thank you guys for your time. I hope you enjoyed the video.